Hi, everybody. So we're going to continue talking about binary today. So I'm going to re-break down the whole, or I'm going to break down the whole binary thing with a little more detail. It's going to start off seeming extremely elementary. Base 10 numbers, I also call decimal numbers. And you're probably not used to the word decimal being associated just to our number system in general. You're used to decimal being like that point where you put numbers after like the decimal point. But our number system is called decimal because, DEC, base 10, or like it's the prefix for 10. Our numbers have place values as you have learned in the past. So for example, if we take the number 365, that is 3 times 100 plus 6 times 10 plus 5 times 1. The significance of this, the reason I'm pointing this out, is that the place values are all powers of 10. So we have 3 times 10 squared plus 6 times 10 to the first plus 5 times 10 to the 1. Nope, 0. My apologies. 10 to the 0 equals 1. So when we do binary numbers, it is the same sort of structure. It's just that our place values are powers of 2. So if we have the number 101, it's completely analogous to the base 10 situation. So we have 3 digits. So the first digit is times, but instead of doing 10 squared like we have here, we do 2 squared because our base is 2. And then our second digit is 0 times, and then again, instead of doing 10 to the first, we do 2 to the first because our base is 2. And then last, we have 1 times, not 10. We're going to have 2 to the 0 because, again, our base is 2. So we are essentially replacing the behavior or the place that the 10 takes up with a 2. So when I'm converting binary to decimal, I'm writing it out, but I'm writing it out in terms of base 10 numbers because 2 is a base 10 number. So we can take this now and expand it, and we have 4 plus 0 plus 1. 1 equals 5 in base 10. We sometimes put a subscript just to represent what base we're working in. So if you see me write a little 2 or a little 10, it's just to clarify that it's base 2 or base 10 number, because obviously, 101 is also a number in base 10. It just means 101 and not 5. So the subscript is sometimes put there for clarity. So back to binary. Let's do one more example. So we have 10111. And in a case like this, I mean, for the previous one, I was able to say, oh, yeah, this is the power of 2 because I just wrote it out for base 10. So I knew, what all the powers were. But I find it easier for myself to just kind of annotate what the different place values are. The first place value, like the one all the way to the right, is 2 to the 0, so that's 1. The next one is 2 to the 1, so that's 2. 2 squared, so that's 4, 8, and then 16. So I like to annotate it just to help me expand the number out. And you don't even have to think of what the powers of 2 are. You just start with 1 and then you just keep doubling it. So you go 1, 2, 4, 8, 16, and so on. So once you annotate it with these numbers below it, and this just helps me to not make mistakes, we can just go ahead and expand it out. And you can expand it out from left to right or right to left. It doesn't matter. But the first one, we know we have 1 times 16 plus 0 times 8 plus 1 times 4 plus 1 times 2 plus 1 times 1. So 16 plus 4 is 20, plus 2 plus 1 is 3, so we get 23 in base 10. Okay, so we have our number here, and we're going to take this and we're going to make it into a base 10 number. So again, I'll, annotate below it with our red. I don't know why this line's here. No, I don't want to call that number. Yeah. Okay, I'll just ignore it. So this is to the 0, so 1, and then we just double as we go up. 2, 4, 8, 16, 32, 64, 128. I know that's not a very legible 128. Let me write sideways now. 256, 512, and 1024. In the previous example, I wrote out everything. I did 1 times 16, 0 times 8, 1 times 4, and so on. But if you feel comfortable, you don't have to write out all of that stuff. Like, we know that 0 times anything is just going to be 0. And we know that 1 times 16 is just 16. So if you feel comfortable, you can also just write this as, okay, 1 times 1024 is just 1024. 0 times 512 is just 0, so we'll skip it. 1 times 256 is 256. 0 times 128 is 0. 1 times 64 is 64. 0 times 32 is 0. 1 times 16. 0 times 8. 1 times 4. 0 times 2. And then 1 times 1. So then we add this up. 1024 plus 16 is 1040. 256 plus 4 is 260. I'm just adding them in a way that I can do it in my head. 1040 plus 260 is 1300. This is binary to base 10. The number 77, and that's base 10, and I want to break it down into a binary number. So I'm going to, again, write out different powers of 2. 2 squared is 4. 2 cubed, 8. I'm going to have to move this 2 to the 5th. So I write out a bunch of powers of 2. And if you want to be sure that you're not like missing something, it's best to write out the powers of 2 until you get something that's bigger than the number that you are working with. Because once you get something that's bigger than the number, you can then answer the question that you should be answering when you're doing conversion into binary. And the question is, what's the largest power of 2 that I can fit into this number? So looking at this, I know that 77, the largest power of 2 that can fit into this number is 64. And then we're left with 10, 11, 12, 13. So what I'm going to do is essentially I'm going to just keep breaking up my number. So 64 is a power of 2. And then I have this 13 left over. So I ask myself again, what's the biggest power of 2 that fits into that 13? And looking at the powers I just wrote down, I can tell you that 8 is the biggest power that will go into 13. And then, we have 5 left over. So 13 breaks down to 8 and 5. And then 5 breaks down into 4 plus 1. So we want to take our number and we want to break it into a sum of powers of 2 by asking ourselves, what is the biggest power of 2 that fits into a number? Once we have this, we have our powers of 2. So we're going to keep writing this to look closer and closer, more and more like our representation of what we had earlier. 64, we know is 2 to the 6th. So this is the same as, sorry, my coughing is making class slow. 1 times 2 to the 6th. And then I'm going to put placeholders in here. We didn't have any 2 to the 5ths, any 32s, and we didn't have any 16s, any 2 to the 4ths. So I'm going to write it as 0 times 2 to the 5th plus 0 times 2 to the 4th plus, and then we have a 2 cubed, which is 8. So 1 times 2 cubed. We have a 2 squared, which is 4. And we have 0, 2 to the firsts, 0 twos. And we have 1, 1. So I've taken this number here and I have expanded it by writing in all of the zeros as placeholders, representing all of the numbers from my list of powers of 2 that didn't make it into this. And I actually could have put an intermediate step in here, and since I, oh my gosh, have some space, I was doing totally fine until I started talking. I'll do an intermediate step in here. Okay. We can think of this as 64 plus 0 plus 0 plus 8 plus 4 plus 0 plus 1. So that doesn't change the value of the number, but I've strategically put those zeros into the places where there could be a power of 2, but there's not. Like where there's could be a 32, but there's not because it doesn't fit, a 16, but there's not, and a 2, but there's not. And the reason we need to put those zeros in there is because when we make our number into a binary number finally, we have 1 in the 64's place, but we need zeros in the other places as placeholders so that, you know, we represent the fact that we have 0 groups of 32 and 0 16s. And then we have a 1 in the 8's place, a 1 in the 2's place, a 0 in the 2's place, and then a 1 in the 1's place. So what I've done in this step is I've essentially peeled off the coefficients of each of these, and I've put them into my binary number. And then we have our number in binary. So the fourth one is 900. And I learned from the last one that I need to leave more space for writing the powers of 2. So our first one is 900 that we're converting into base 2. So I'll list them out again. 2, 0 is 1. I listed out my powers of 2, and again, I went 1 bigger than the number that I have here. 1024 is not going to go into this number, but 512 will. So I take my number, I break it down as 900 equals 512, and then what do we have left? We have a little less than 400. We have 388. And then I take my 388, and again, I ask myself, what's the biggest power of 2 now that goes into that? And that's going to be 256. If I pull off that 256, I'm left with 132. And I can see that 128 goes into that. And if I take 128 out, I'm left with 4. Okay, So after I pull out that 128, it breaks down into 128 plus 4. So we've reached a point where all of our numbers are powers of 2. If they weren't, we would just keep going until eventually all our numbers would be powers of 2. We have 512 plus, and then I'm going to put those zeros in as placeholders again. Well, we have 256. We have 128. But what we don't have represented here is 64. We don't have 32. We don't have 16. We don't have 16. We don't have 8. 64, 32, 16, 8. We do have 4. We don't have 2. And we don't have 1. So this is the same as 1 times 2 to the 9th plus 1 group of 2 to the 8th. 1 group of 2 to the 7th. Four, which is 2 squared. We have 1 group of 4. 0 groups of 2 to the 1. And 0 groups of 2 to the 0. So what this comes down to now is 1, 1, 1, 0, 0, 0. So again, I'm just pulling these guys off and writing them down. 0, 1, 0, 0 in base 2.